Yeah, just super excited and honored to be here with the delegates and the team to really introduce and demonstrate Session Smart a bit and talk about its integration with Mist and for starters here I'm gonna, like was mentioned earlier, some of you may have seen, past Network Field Day with 128 technology. And so some of this may be a little bit of a refresher, but, really wanted to set the stage here for those that may have missed it. And talk about Session Smart, what it means, where it came from, and why it's here now with Juniper. I personally enjoy talking about this journey of Session Smart technology and secure vector routing because I was really lucky enough to have a front row seat through all of it, most of its creation. So to start with, let's rewind the clock a bit back to 2015 or 2014, actually, when this tunnelless technology that we're going to talk about here was first being created. Now, you panelists in the audience will remember that, back in 2014, SD-WAN really wasn't that much of a buzzword yet. SDN and NFV were kind of the hot topic or the hot buzzwords, kind of climbing the hype cycle and arguably the tools of software and software defined were still looking for a useful marketplace landing with broad acceptance and utility. So of course, in hindsight, we all know that place would ultimately turn out to be the WAN but not a lot of people were talking about it at that particular time. Now, back in 2014, the folks that were working on this technology not only had a background in IP routing, but also in IP telephony. So they kind of looked at networking through a slightly different lens. For instance, with an IP voice and video application, they operate inherently with the notion of a session. And so in that world, I pick up the phone and initiate a call to you, and there's this signaled session that gets established. And there's a directionality with that session, me to you, and based on that, a symmetry in the conversation progresses as we exchange information. And truthfully, this is the way most applications work. So this approach to sessions where there's a signaled exchange establishing intent and the dispossession of the network towards the session were some of the formational things of the technology. But at the time, while networking was certainly seeing some notable changes that it hadn't seen in a very long time, thanks to kind of being reinvigorated with the powers of software and software defined, the IP routed networks that everyone was building upon were largely built and operated the same way they had been for the past 20 or so years, as shown in the slides we see here. The routed networks were born out of a theory that said, hey, keep the networks stateless, leave security to the endpoints, keep it fast and simple. And of course, this was obviously for really good reason. In the early days when RFC 1717 was being drafted by the long bearded wizards of the ITF, it was all the internet could do to really keep up with the booming demand for networks. So, based on the technology of the day, making it go bigger and faster were the most important things. But bottom line, routers started out simple and stateless. So, if that was the reality or the theory in the beginning, in 2014, when this technology was sort of germinating, this was the reality that we lived in. As the networks grew and the internet took off, high value targets such as financial institutions, governments, and everything, started to put things on the network. And it turns out security was needed within the network. And so firewalls got loaded on top. And to keep up with the distribution of load and scale applications, load balancers and other stateful devices were piled on top. And as the networks were not the routed networks anyways were not smart enough to take packets where they needed to go. Tunnels and overlays proliferated to get them where they needed to go. So if the networks were envisioned to be simple and stateless, they had become anything but that. State was everywhere, and complexity really was the result of it. So, for the majority of the industry wielding the power of software and software defined at that time, they were busily focused on taking the same approaches and the same architectures they had done previous, and just kind of recreating them in software, which really, was only compounding the problem of fragility and complexity that was festering. And really for just marginal gains in end user experiences. So the only medicine that was being applied to this malady from our perspective was putting packets into tunnels to get them to go places the routed networks weren't smart enough to take them, and sprinkling a heavy dose of orchestration and automation on top of it. To that team back at the time, that was the definition of technical debt, and networks everywhere were just accumulating it. So the motivation was a feeling that what was being done just wasn't enough. If all we did was take the same things we did in hardware and do them in software, we were just doing it wrong. So, the promise and vision of software and software defined, of unlocking innovations and networking to power next generations of networks, improve user experience, they just weren't going to be realized to their fullest potential on the current trajectory. So that was the mindset, and some of the formational thinking behind the Session Smart Router, and at the time it was conceived of. So they set out to build a router, a smarter router, and there were a few key things that they decided a smart router needed to have. First of all, it had to make the best possible use of software and the powers of software defined. There's that famous saying that says software is eating the world, and it's for good reason. No hardware can compare to the rapid innovation cycles, the superior economics of software, and the platforms that power software, from small to large to cloud, and the economics of them really had to be leveraged well. Secondly, it had to operate based on sessions. In the journey from client to cloud, sessions are the thread that connect the users to the applications. So a certain amount of that network state that was just being kind of piled on top in all these uncoordinated middle boxes just needed to be democratized into the routing plane in a manner that was well coordinated across the routing nodes. And, not just for the purposes of an evolved and better synchronized control plane, but also for the purposes of telemetry, which plays an important role in some of the stuff that we're going to see as we get into Mist. So also, the way the network was designed and operated, kind of that day zero experience, it really had to orient around services, not IP ports, prefixes. The network constructs themselves had to orient around services, because that's what, without services, what's the point of a network? It's there to deliver services. And last but not least, security had to be baked in, not painted on in perimeters and zones and things like that. It really, an element of native zero trust had to be kind of baked in at every hop. So that's more than an adequate setup and intro to the technology. Let's jump right into how it works and operates. So in the diagram here, we got a simple topology of basically two SSRs with a cloud in the middle, some network, some layer 3 network in the middle. And we're going to kind of walk through a packet as it flows through this, and talk about secure vector routing and how it works. I'll point out as we go through this that this is a simple setup of two SSRs. Could be a simple hub and a spoke at a data center, or a hub at a branch, or a hub at a data center, spoke at a branch. But this was designed and intended for multiple hops, so there could be potentially many SSRs kind of in this middle bit. But we'll start simple here, and we have a source and a destination at the left and the right, source IP address, destination IP address, and it sends that packet into the SSR at some point. Ideally, this SSR is the default gateway for this this source client here on its LAN. The very first thing that SSR is going to do is detect, first of all, whether or not this packet is part of an established session. In this case, it isn't. It's the very first packet that we've seen for this user and for this session. So we're going to associate it with a set of services and policies and tenants. Now, the tenant is who the user is. We're going to decide. We're going to decide who this user is, and ultimately, does he have access to the services that this packet is destined for? And then finally, we're going to determine the policies that are associated, like how we're going to deliver this session to the next hop, and ultimately onto its destination. In this case, we determine our next hop is going to happen via another one of our SSR brethren out there in the network, the one on the right. And so we will go ahead and forward that packet out onto the wire. And now we will effectively NAT the packet. So now the packet is no longer from source to destination. It's from waypoint 1 to waypoint 2. And this is effectively just a NAT of the packet. We NAT the IPs and the ports associated with it. And the original source and destination port and protocol is encapsulated in a little bit of metadata along with the associated policies that were decided upon at this first router. It's cryptographically signed, and it's sent out onto the wire to traverse this network destined for waypoint 2. Ultimately, it finds its way to waypoint 2. Waypoint 2, first of all, validates that it is authentic, that it's secure, and then begins to inspect the policies that were decided, and it turns around and programs its forwarding plane for the rules that were decided on for this session. And ultimately, the packet comes out the other side, source and destined to and from the end endpoints in source, in destination, as if there was nothing in the middle. As this session progresses, the metadata is effectively shut off. Once the forwarding planes are all programmed in one or more SSRs in this path, they can shut off metadata at that point. So then it's just effectively a NAT, no encapsulation, no overhead, and the good put of that session is really maximized because it's just a simple NAT at that point. And because this is a network field day, let's actually look at this in action. So what we're going to see here is a packet from our endpoint at 192.168.10.10 going to 10.204. This is the original packet, that first packet hitting the first hop SSR. And here it is egressing the first hop SSR. So what you see here is that little bit of metadata that I mentioned that's kind of stuck, on the end of the transport header. And in this particular case, we've actually decrypted the metadata here with our dissector, so we can see some of the elements of it. But we see that original source and dest IPs and ports and all that good stuff. And we see the tenant that was assigned. This came from a user in our finance segment. The service is inventory new. That's the name of our service. It has, associated policies, and, we're headed for our peer. So it transmits across the network. This is ultimately arriving at the next hop peer. And, we see it actually goes through multiple hops before finally it comes out the other end and the metadata is removed. Now, yeah, go ahead.
This is Aaron Conaway.
Yep.
How are the users and the tenants detected? I guess the tenant's probably from the user, right? But how is the user identified?
Yeah, great question. Ultimately, there's a variety of ways that user tenancy is identified. Probably the simplest way is similar to like you might do on a zone-based firewall, where you have an interface, a VLAN or something like that, that is the gateway for a collection of users, and they're matched, based on their ingress point into the network. So that's kind of the simplest way. There's some more advanced ways, like we can do source prefix matching. Say all these packets are flowing into a router and there's multiple different segments for which it's not the gateway and it's kind of further back in the network. We can do source prefix matching to figure those out. And then we have some prototypes of even some more advanced things where we actually have drivers on an endpoint, like on a Windows device, that will actually associate the user to a tenant and actually put metadata right in the packet. So that packet could almost enter from anywhere, and that tenancy would be established by a driver right on the endpoint. That is a prototype. I can't go into a whole lot of detail on that one, but the implementation, there's sort of the way that we identify tenancy today in the implementation, but certainly the protocol and the technology was always designed where this tenancy could be established in a variety of ways, and ultimately once it hits the router, and then that tenancy feeds into the services and the associated policy. Great question.
All right, thanks.
Hey, Reid, I've got a question for you as well while your flow is broken. So you're looking at the packet capture here and looking, down the stack here. Am I reading this right? Is the 128T, is that payload, or is that somewhere else that you guys are putting that in header data? Where does that sit exactly?
Yeah, to a router in the middle that didn't understand metadata, it would look like payload. It's right after,
Gotcha.
It's put right on the end of the transport protocol. You'll note here that our source and dest ports are different. They're changed as well. So, here's waypoint 1 and waypoint 2 of the routers that, in the fabric that this is, heading to and from. One unique thing about this technology is every session in equals a session out, meaning, if when you think about a traditional tunnel, it's going to kind of stack up all sessions in and to devices in the middle that may be doing ECMP based on flow hashing or something like that. Often they will have problems with that because it will all look like, port 4500, port 4500 or something like that. The 5 tuple, basically the outer five tuple that we see here, ultimately becomes a flow key, not just for the end SSR as it enters the SSR that it's destined to, but other devices in the middle will see these as unique flows as well. They'll distribute load and everything, and you kind of prevent some of those elephant flow problems that you can get in other places.
So just a couple clarifications. So this packet is sent like at intervals to identify the flow, and then you've got whatever your user payload data is, or are you borrowing from the payload in each packet to make sure this metadata is encoded? How does that work?
Yeah, so this what we'll see here, I'm going to kind of go down through a few of these here. There's that forward metadata in the first packet of a flow that would again program the forwarding planes for one or more SSRs in the path. And as this flow progresses, you're going to see in the reverse direction, there's a little bit of metadata sent in the reverse direction. And that metadata will sometimes it'll include things like state of like load state of the next hops. They're kind of talking to one another here.
Got it. So like it's an as needed. This is sent as needed as you're needing to take action in the forwarding plane.
Exactly. Once this is established, there's no metadata. It's just there's nothing there.
Gotcha.
As you alluded, there's instances where a little bit of metadata will be turned on. Say we need to move a flow to a different path, just turn on metadata, move to a different path. Maybe there's other kind of flow maintenance tasks that will happen from time to time, but ultimately, unlike a tunnel with full encapsulation, this metadata represents a pretty much insignificant amount of bandwidth in the overall life of most flows.
Gotcha. One more question, and then I'll let you go. So what are the implications for IPv6? Specifically since you don't have fragmentation, and mobile networks are on the rise. I think we went over 51% of mobile usage in the U.S. in December for internet. So we're more mobile than we are anything else. And you've got some slightly reduced MTUs when you're dealing with IPv6 payloads there. What are the implications of that when you're obviously you're trying to build an SD-WAN connected ecosystem, which includes mobility devices a lot. Yeah. How does that play into IPv6?
Yeah, I mean, ultimately, our first, the step one is we try to prevent fragmentation at all possible when it's required. Obviously, the transit networks in the underlay can be IPv6. You can have IPv6 in the outer. You can kind of weave in and out of IPv6 and IPv4. But one of the things that the routers do as they detect paths between one another, they will actually monitor. There's kind of a process where they discover the path. Say it's an IPv6 network. They discover the path between themselves, and they will actually probe and discover things like MTU size and kind of understand if there's stateful devices in the middle that could be impacting or causing issues, and then it'll deploy prevention, and traversal mechanisms as needed. So, in the case where you have a network in the middle that does require some fragmentation, we don't. In that fabric, we don't do a traditional IP fragment. It would look on the wire like a UDP packet, but it transmits ultimately sort of invisibly across that. Even if we'll take, say, that one oversized IPv or TCP packet and then transit it across the fabric broken up into two UDP packets.
Got it. Okay. Thank you.
Do you guys spoof like path MTU discovery so that doesn't actually have to happen on an end-to-end discovery basis? Because the MTU sizing that you could do sort of end-to-end, so that way end hosts, when they're negotiating, sort of to Kevin's point, right? You can just answer back quickly and tell them what sizing set you want, and then because you guys are fragmenting internally, it doesn't matter. Right?
Yeah, exactly.
Can you actually do that? Do you actually spoof path MTU for V6, or is it not something you do?
Yeah, we don't spoof it currently, but again, most times because we sort of make that invisible to the end devices for the most part. We do some things like MSS clamping, where we will intelligently affect MSS. Again, just to make it more efficient and avoid fragmentation if at all possible. But we don't do that with the path MTU at this time.
What are the control mechanisms that kind of would prevent users from being able to kind of spoof their own source routing?
Yeah, ultimately this is where we get into the full stack and some of using some of our APs and switches as well with the full stack and Juniper. We are able to delegate a little bit of that to the wireless and wired access. So by in a lot of these environments, by the time it hits the SSR, there's already been some element of access control relevant to whatever their access mechanism is.
Thanks.
All right, so let's just keep it moving here. So so that's kind of an overview of SVR, secure vector routing, the protocol, how it works. But how does this actually get deployed in real life, and where do you put it? How does it drop into existing networks? Really, as the routers are deployed at branches and data centers and cloud edges, those waypoints that you saw, they kind of appear and become strategic points in the topology to form an overlay fabric. And the Session Smart routers themselves are software based, like we mentioned, running on x86 platforms, and they leverage kernel bypass technology, namely DPDK, to streamline the components of off-the-shelf hardware for performance and latency. And while the software itself runs on commodity white box platforms, we have a versatile set of certified platforms that we rigorously and continuously test in our automated test environments to give the highest levels of assurances for functionality, performance, and support. So the software scales up and down for small branches, small offices, to large hubs and interconnect points alike. And so, at the end of the day, it forms this this service-centric fabric that becomes the SD-WAN. Now, at the end of the day, software does need hardware to run on. And as we alluded to at the beginning of the presentation, we're excited to be introducing a branch appliance for the SSR. This is the SSR 100 line. These are SSR 120 and 130. These are great small to medium branch appliances. And really our aim with this is to simplify how we get Session Smart routing into customers' hands. Now, first party platforms aside, the openness and flexibility of the software remains a really huge part of Session Smart routing. I mean, at the end of the day, platforms are simply a vehicle to get Session Smart routing into more places so networks and users can start enjoying the benefits. And here you see some of the portfolio of third-party options, some of the benefits here in this era, current time, as you guys know, with crippling supply chain shortages all over the industry. We've really seen that thanks to this ability of software and the ability to run on more platforms, we've really been able to weather the storm much better than most. So that's kind of hardware and a blast through Session Smart routing and where it came from and what's it all about. And of course, we're using that at the end of the day to deploy an SD-WAN.